Hi guys, welcome back. We're going to continue today with atomic theory and bonding. So we're just going to pick up where we left off last day. Before we do that, can you throw in some check marks there so I know you're with me and everything's working okay? And we'll continue on. Perfect. All right, so last day we were just starting into chemistry. And from what some of you guys were saying, it seemed like just about everything I covered last day was a review from grade 9, which is a good thing. So hopefully I refreshed your memories and you guys are all, ready to get into some, maybe a little bit, some new stuff today. So what I'm going to do is I'm just going to jump through this. We talked about elements, compounds. We talked about the relative sizes of the particles. And then I said this was the most important slide of, chemistry. If you guys can, master most of the stuff on here, which is all stuff you probably learned in grade 9, you'll be really set out on the right path. So you should be doing okay. So the important things here, the atomic number is the number of protons, and every time you change the atomic number, you get a new element. So that defines what types of elements we have. The atomic mass is how massive the nucleus is. Remember, the protons and neutrons are really big compared to electrons. So when we add the mass of an atom up, the electrons don't really have much of an impact on the mass at all because they're just so small. So when we have the atomic mass, how much the atom weighs, it's the protons and neutrons in the nucleus. So remember the two numbers that are important on the little boxes on the periodic table. You have the atomic number at the top, which is the number of protons. The atomic mass is protons and neutrons together. So if we subtract those two, we end up with the number of neutrons in the element. When we left, we were just talking about ions a little bit, and I didn't really get into it as far as I'd like. So Taylor will get going. So we talked about periodic table, what it looked like. We did some Bohr models, and you guys will be expected to know the first 18 elements in terms of Bohr models. Went over the rules of Bohr models. Protons and neutrons get written in the middle circle, and you start filling your shells. Start at the inside, work your way out. First shell contains 2 electrons, second shell is 8, third shell is 8. That's as far as you need to go in Science 10. And we discussed it for just atoms at first, and then we will start talking about ions here in a second. So ions are atoms that have a charge. So if the number of protons and electrons is unbalanced, you end up with an ion. So if an atom has a charge, we don't call it an atom anymore. We now call it an ion. So we looked at the 2 examples here. Element 11 was sodium. Yes, sodium. And you can see that sodium has 1 electron in its outer shell. And then is it going to be easier for that sodium to gain 7 electrons to fill its outer shell or get rid of 1? It decides to get rid of 1 because that's easier. Now it has only 10 electrons but 11 protons. So because it lost an electron, it gains a negative charge. Sorry, a positive charge. It loses a negative. We looked at fluorine. It gains an electron. And then we started talking about patterns in the periodic table. And I believe this is where we left off. A few questions in chat. So what page is our starting point? I'm not exactly sure what page this is, Taylor. Maybe you can find it and put it into chat and everybody else will know. But we're at patterns in the periodic table. Alex was asking what is light made of, and photons was the right answer, Ava. So yeah, lights, photons, same thing. And Avery has a question from the learning guide. You want to fire away there, Avery? I can jump over to the learning guide right now if you want. Three questions from the learning guide. Alex, no, they'll never gain 7. Okay. I'm not sure. Page 7. Page 9 at the top of the page. Draw Bohr atoms, write the protons, neutrons inside. Max number of electrons allowed each shell. Am I on the wrong page here of the learning guide? At the top of the page, what does it mean for relative mass? Wrong one. You said page 9. I'm on page 9. Top of the page. Maybe yours printed differently. It's question 3. Oh, here. The relative mass. That was referring to the chart in the notes. Basically, protons, neutrons, and electrons, I'm going to get this wrong. If you said an electron has a mass of 1, how many electrons would it take to make up a proton or a neutron is essentially what it's asking. So protons would, I think they're 1836. I'm going to go back to the notes just to verify that. I'm just going off the top of my head. It's right here. Yep, 1836. So the mass relative to one another is basically what we're talking about here. So if an electron weighed 1 of something, 1 mass, to make up a proton, you'd need 1836 electrons to equal the mass of 1 proton. And the same thing for the neutron. So a neutron and proton are really close to being the same weight. So that was that. So relative mass 1836, 1836, if the smallest one or your electron is listed as a 1. So hopefully that helps. Is there any time when the gain, 3 questions? Nope. Anything else from the learning guide that you guys wanted to look at before I continue on with the notes? I had asked you guys go through these, and there's a few questions on Bohr models and atoms and ions that you should have looked at. Why is oxygen considered an element but water is a compound? It's an interesting question. So oxygen is just O2 when it's by itself, and water is H2O. So what's the difference between O2 and H2O? No worries, Abby. I'll get to them in a second. So in H2O or water, you have 2 elements together. So water has hydrogen as well as oxygen. So we have 2 elements form compounds. Whereas oxygen on its own is just 1 element. So hopefully that helps you out a little bit, Taylor, and everyone else. When could we do question 10? Was that the one I told you to skip, I think? Which type of atom can form a covalent bond? Yeah, we'll get to covalent bonds probably at the end of today's class. So you should be able to answer number 10 by the time we finish today. Just depends how far we make it. I don't want to go terribly fast through everything. All right, so we got down to there. All right, Abby, let's... 3 question. 1, do you prefer the Bohr model if there's, say, 3 electrons in the outer shell? Do you prefer us to do it like north, east, southwest, or spread it out evenly? That's a good question. So let's look at something that has 3 electrons in its outer shell, like boron. So boron is element number 5, so it has 5 protons. It has a mass of 10.8, it's 11, so it has 6 neutrons. First shell has 2 electrons, and its second shell will have 3. I'd probably start here and write it like that. You want to keep them all separate if we had an extra one, and then start pairing them up in the second shell. They'll actually form pairs in real life too. So Yeah, it's a great question. Just rate them as, there you go. Go like north, then east, then west. If you put it north and east and south, sorry. If you put it on this side, that's fine as well. I just kind of, I don't know, when I'm thinking kind of like a clock, start at 12 and I go that way, it's just kind of habit, I guess. It's nothing, no rule that says, hey, the electron has to be on the right side. You'll see these things drawn in all sorts of different ways. It doesn't matter where that electron ends up. So just preference. Try to be consistent with how you do it. Stick with it. That way you'll make fewer mistakes. So that was the first of several questions. 2, for ions in the Bohr model, do you like us to put example 2 plus or plus 2? Again, it's just kind of whatever is most natural for you. If I were to write in a Bohr model, I always go plus 2. I'll always write it like that. It's just a habit. That's how I've always done it. In some textbooks, you'll see it as plus 2. Sometimes you'll see it as 2 plus. It just depends on the textbook. I will always write it as minus 1 or minus 3 or plus 3. I'll always write the sign first and then I'll write the number second. This is just my preference. That's how I learned how to do it, so I'll stick with that. What else do we have for questions? Could we please go back to the Bohr model so I can write down the rules? Yeah, for sure. Okay, what chapter will the midterm go up to? That's a good question too, Avery. I have a feeling we'll finish, I'd like to finish chapter 4 before we get to that midterm. Basically, whatever we finish at the end of next week, that's kind of where we'll cut it off at. So I think a natural break would be 4, but I can't guarantee we're going to make it that far. And then Taylor will get to the brackets because we're going to spend a bunch of time talking about that today, Taylor. So Avery, to answer your question more thoroughly, we're going to do chapters 1, 2, 3 for sure, 10 for sure. So 1, 2, 3, and 10. Those are all the ones we've covered up to the March break. We'll likely get through 4. So I hope to have 1, 2, 3, 4, and 10 on the midterm. But that's just depending on how fast we get through today's stuff. So let's go back to the rules for the Bohr models. And then we will move on in a second. Some good questions. Thanks for asking all of these things, guys. Bohr model, where are you? There you go. So there are the rules for the Bohr model. And I'm assuming that, I don't know for sure, but I'm assuming that the Bohr model is actually a learning outcome of grade 9. That's why it's not covered in the online portion of the course. But it's something that's so important because we spent some time looking at it that we really should know the rules and write them down again. Why is it called the Bohr model? It's named after Niels Bohr. He was the guy who came up with the idea of this Bohr model. When we talk about atomic theory through history, different people have come up with different ideas as to what makes up all of the stuff that is you and me and everything around us. And the ideas were named after the people. So today we're going to cover something called Lewis dot structures, which are really, really similar to Bohr models, but they're named after a different guy. His name is Lewis. When you talk about atomic theory, one of the pioneers on atomic theory, his name was John Dalton. So Dalton had his theory of an atom, and I think they define it, or it's kind of like everything was kind of like blueberry muffins, where people understood that things were made up of these really small things, but they didn't really know how to describe them. So Dalton thought you have this muffin, that's your atom, and then the blueberries, the electrons and charges kind of float around on the inside. And then Bohr said, hey, you know what, I think the electrons are actually on the outside, and that's how we evolve these kind of theories to where we are and what we understand now. String theory is cool. String theory is way beyond this course. I have a physics degree. I don't even think I talked about string theory until like third or fourth year of university. So not something that you'll cover very quickly in your careers. Yeah, so you learned about all those people last year. Usually I cover it, but it wasn't in the course so far, so I just skipped it. Because it's not on the exam, it's not important to know for grade 10. I mean, it's important to know, but it's not covered on the exam. All right, so periods in the periodic table or patterns in the periodic table. Remember, we call the horizontal rows, we call them periods, and then the vertical columns we call groups. So we're gonna just look at some really cool things that happen as a result of the organization of the periodic table. Now, periodic, a periodical, if something happens periodically, what does that mean? Well, that means that it happens on probably like a semi-regular basis. A periodical is like an article that's published usually like 4 times a year, 3 times a year, periodically. Periodic table shows things that are repeated periodically. So for the Bohr models, these aren't true Bohr models because they don't have protons and neutrons in the nucleus or the middle. They have the symbols for each of the elements instead of protons and neutrons. But you can see how the patterns repeat each other. And I think this is pretty darn cool. I don't know if anybody shares my enthusiasm about the periodic table, but the first row, and again, this periodic table's kind of been cut and squished together. Oh, gotta be careful with this mouse. All right, so the first row has 2 elements in it. The first shell holds 2 electrons. So once you fill that shell, you start in the second period or the second row. So lithium in its outer shell has 1 electron. Second column, 2 electrons. Third column, 3. And Abby, this is kind of getting back to what you were asking earlier. You notice the third electron's written over here and they're paired at the top. It's just preferences how the textbook draws it. Fourth column, 4. Fifth column, 5. Sixth column, 6. Seventh column, 7. Eighth column, 8. And then it's full. So what happens? Well, we need a third shell. And you go across and you fill up your shell 1 electron at a time until you go to the fourth shell. And this pattern repeats for the entire periodic table. Electrons fill the shells. The shells get more complex as you get lower down in the periodic table, but it's still the same pattern that's repeated. So yeah, Alex, for sure. That's a great way to kind of put it in the form of a question. You can put the electrons wherever you want. Generally speaking, we'll go north, south, east, west. So try to put them at the up and down and left and right. But if you put like 2 at the top and 1 on the side, kind of like looking at boron here, that's fine. I can count when I look at them, so I'll be able to figure it out. It's just different textbooks and different people do it different ways. So there's no real, I don't know if there's an official way. If there is, I'm not aware of it. So one cool thing about the periodic table is if you wanted to know how many electrons are in the outer shell of an element, let's say I picked element 7 here, nitrogen, right next to me. Well, if it's in column 15, its outer shell has 5 electrons. If it's in column 16, its outer shell has 6. 17 has 7, and 18 has 8, with the exception of helium, because helium can only hold 2. So again, the periodic table that you're looking at here is kind of, chopped and squished together. On the periodic table, you're looking at the first 18 elements. There's kind of the step in the middle here where this kind of gets cut and squished together. So it's just makes things a little bit more compact, but those are some really cool patterns in the periodic table. So the last digit of the group tells you how many electrons are in the outer shell. And that will be really important when we start talking about Lewis dot diagrams. The only exception is helium, because helium's in the 18th column, so you'd think, oh, maybe it has 8 in its outer shell, but that first shell only holds 2. So that's where you run into one exception to that rule. Now, I don't love where this kind of slide falls into place, but we'll just go with it and we'll talk a little bit more about it. And Taylor, I haven't forgotten about your question about the brackets, so we'll get there. eventually. So we're going to talk a little bit about forming compounds today and how that works. So basically when atoms get close together, last day we said, oh, it just gains electrons or just loses electrons. Well, it only really happens when atoms get close enough to something that's trying to get rid of or gain electrons, where the electrons actually get transferred. And when they get transferred, because those atoms are now ions, they have a charge, sometimes they'll stick together and they'll form compounds. So that's how we form compounds. The valence electrons, the outermost electrons, are the things that determine whether atoms will combine together or not. Sometimes they're compatible, sometimes they're not. It just depends on their outer shells. So metals lose electrons, non-metals gain electrons. We'll spend some time looking at that here in a second. There's two types of bonds, so we can talk about ionic bonds and covalent bonds. So an ionic bond forms when electrons actually get transferred from one atom to the next, and you get positively charged atoms, or ions, I should say, and negatively charged, and they stick together because positives and negatives attract. Covalent bonds are a little bit different because they're actually sharing electrons, and this happens a lot as well, but we won't probably get to covalent bonds quite yet. Maybe at the end of the day. Realize we don't have a ton of time. Get through as much of this as we can. All right, so we're going to look at ionic bonds first, and then we'll get to covalent bonds in a second. And we're going to look at them in a couple different ways. And basically most of Science 10, or most of the chemistry portion, is developed on the idea of these compounds and naming them, and then chemical equations and things like that. So we're going to spend lots of time looking at these over the next little bit. So here's a couple of Bohr diagrams that shows oxygen and lithium. And when these things encounter one another in real life, lithium is element number 3 on the periodic table, and it has that one electron in its outer shell. So it's not going to gain 7, it's looking to get rid of 1. And then oxygen's kind of floating around too, and oxygen, you can see here, has 1, 2, 3, 4, 5, 6 in its outer shell. So oxygen's looking to gain 2 electrons. Well, what do you know? Lithium here is looking to give up 1. This lithium's looking to give up 1. So the oxygen takes those 2 little X's from lithium, and it gains those 2 electrons. And then lithium, because it got rid of those electrons, is now positively charged. Oxygen gained 2 electrons, so it's negatively charged. And because negatives and positives attract, the oxygen and the lithium, they stick together, and it forms a compound. And there's 2 lithiums for every oxygen. So where did the 2 lithiums come from? Now, remember, atoms are really small, and when we talk about atoms, there's millions and millions and millions of them interacting. Even in a really small sample, if you mix them together, there'd be trillions and trillions and trillions of atoms mixing. So there's always going to be more of whatever's there. So when we're talking about lithium, we're like, how come there's 2 lithiums for every 1 oxygen? Well, it just happens that there's a million lithiums there, so the oxygen just takes 2 of them and they combine together. So let's do a couple examples of this. Again, this isn't in the notes. I would love it if you had like a blank piece of paper or something next to you. So let's see if we can figure out how these things combine together using the example of sodium, which is a metal, and then chlorine, which is a non-metal. So I'm going to jump over to my OneNote kind of blank page, because I can't write on this, unfortunately. Let's create a new page here. All right, so the example is sodium and chlorine. So what I want you guys to do is draw the Bohr model for sodium, which is Na on the periodic table, chlorine Cl. I want you to draw sodium here, and chlorine here. And then once we've got those, we'll figure out what's going to happen with the electrons and getting into the brackets and how those work and everything like that. So first thing you want to do is draw the sodium atom. We'll start with an atom. And then the chlorine atom as well. So that means the number of protons is going to be the same as the electrons. So go ahead and do that. I'm going to give you guys a 30-second head start, and then I'm going to do mine as well. Grab my trusty periodic table, which you should have with you at all times. You should take it with you to the dinner table. Never leave home without it. Just joking. All right, I feel like that was 30 seconds. Sodium on the periodic table is number 11. So it has 11 protons. And sodium has an atomic number of 23. So 11 protons, the mass of sodium is 23. So 23 minus 11 gives me 12 neutrons. There we go. So 11 protons, 12 neutrons. It's really small for you guys. I'll make it a little bit bigger. 11 protons, 12 neutrons. All right. If I have 11 protons or 11 positive charges, I'm going to have 11 electrons. So I'm going to have my first shell is going to hold 2, my second shell is going to hold 8, and then I'll probably have 1 electron in the third shell. Here we go. First shell, 1 electron, 2 electrons. So 11 protons is 11 electrons. Second shell, I have 1, 2, 3, 4, 5, 6, 7, 8. So that takes me up to 10 electrons. And I'm going to draw one more. And I'm going to put it over on this right side because I'm going to draw chlorine over here in a second. And I want them to be close together. All right, so there's sodium. Let's do the same thing with chlorine. Chlorine on the periodic table is element number 17, so it has 17 protons. Has a mass of 35.5, so we'll call that 36 minus 17. I think we drew this guy yesterday even. So there's my nucleus. All right, so first shell has 2. There's 2. Second shell has 8. 3, 4, 5, 6, 7, 8. And then my third shell, because I have 17 protons, I'm going to have 17 electrons. So I've drawn 10, and I need another 7. 1, 2, 3, 4, 5, 6, 7. Whew. All right. So there we go. We have atoms drawn for these two things. Hopefully you guys managed to get that far. That's kind of what you would have encountered in grade 9. Bohr models for the atoms. Now, we're kind of moving into grade 10 now, and we're asking ourselves, how are these things going to combine together? Now, this sodium and chlorine are kind of a really basic example, but if we look at sodium, it has 1 electron in its outer shell. Just the 1. Chlorine has 7 electrons in its outer shell. It's like a match made in heaven. The 1 electron here from sodium, it's going to try to get rid of that 1. And because the chlorine is looking to gain 1, well, it's going to gain 1. So remember, sodium only has 1 to get rid of, and it's going to give it to the chlorine. So it's going to end up filling in that 1 missing spot. So what happens is, because it's looking to get rid of 1 and chlorine's looking to gain 1, they're really happy because they're going to get rid of one, it's going to gain one, and everything's going to be great in the end. So let's just keep looking at what this turns out to be like. And Abby, you are really correct again. Yes, it changes the name of it to sodium chloride. And we'll talk about the rules for naming next week for sure. All right, so I'm going to draw these things a little bit closer. Try to make it a little bit neater. Still waiting for my fine motor skills to develop, although I'm giving up hope. All right, first shell holds 2. Perfect. Second shell holds 8. There we go. And that third shell only had 1 electron in it, so it got rid of that outer shell. And because it got rid of that 1 electron, we end up with a bit of an imbalance. So we need to ask ourselves, how many protons do we have? Well, we have 11 protons. How many electrons do we have? We have 10 electrons. So if I am sodium, what charge will I have overall? Well, if I have an extra positive, I have an extra proton, that means that this sodium, what we used to call an atom when the protons and electrons were the same, well, it got rid of one of the electrons. So now the protons and electrons aren't the same, so it's now called an ion because it has an overall charge. And this is why we put the brackets around it. Getting back to your question, Taylor, from the beginning, we put the brackets when we've lost or gained electrons to show that it's no longer balanced in terms of protons and electrons. It's gotten rid of an electron. So now it has an extra proton. So up in the top here, I'm going to write +1. And I'm going to write +1 because it has 1 extra proton. So because it lost the electron, it actually has an overall charge of +1. The charges are imbalanced by 1. It's not always 1, but in this case it is. Let's look at the chlorine. What happens to this guy? So the first shell has 2, the second shell has 8, and then in this case, I need to draw a third shell, because that third shell is now full. And Abby, I'm thinking that even abstract artists need fine motor skills. So I've given up on art in general. I'll stick to things like science. All right, maybe I'm going to change the color of one of these electrons here, just to show that it came from the other one. So the chlorine now has an extra electron. Before it was balanced, it had 17 protons and 17 electrons, but now it has 17 protons, and now it has 18 electrons because it gained that extra electron. So overall, this guy now has a charge of -1. So the charges have to balance. If you have +1, you can have a -1. If you have +2, well, you're going to need 2 of that other thing. So it gets a little bit trickier, but this is the general idea. So it's taking into consideration the idea of ions. Now, because these things are oppositely charged, overall, they stick together and they form what we call as a compound. And a few of you guys were thinking, oh, in grade 9 we learned a little bit about naming. So normally it'd be sodium and chlorine, but when we combine them together, we change the ending of chlorine to chloride. You've gained an electron, Taylor. So if we look down here at the bottom, we have 17 positive charges and 18 negative charges. So the overall, the extra 1 that we're dealing with is an electron. So we have an overall charge of -1. You've gained a negative charge in gaining an electron. Before it was balanced, you've gained an extra electron, now it becomes negatively charged. So that's sodium and chlorine. So that's a pretty kind of a basic example. The Bohr models are a bit complicated because they have tons of electrons buzzing around, but the idea of bonding those things together is pretty straightforward. I think I have another example and then I'd like to go through. Yes, I don't, but let's pick a different one. Let's do one more. I know this stuff takes a while, but I want you guys to have a good sort of foundation in doing this stuff. While I'm here, what I will mention is, if you look at the periodic table that you guys have with you, sodium, I might as well jump to a periodic table here. Sodium, over here, has this charge in the top right corner of it, and that charge is plus. It just says plus, but it's +1. So remember, sodium always has one electron in its outermost shell. So when it forms an ion, it's always going to get rid of that electron, and it will always have a charge of +1. So where does the +1 come from? Well, sodium, because it's getting rid of that one electron all the time, it always gets rid of 1 instead of gaining 7. Because it's always getting rid of 1, it's going to end up always having a charge of +1. And then we use chlorine as our nonmetal over from this side. And chlorine has a charge of -1. Why does it have a charge of -1? Well, remember, its outer shell always has those 7 electrons in it. It's always going to gain 1 extra electron and have a charge of -1. So everything that we deal with, in terms of the first 18 here, their charges always work out really nicely. When you get into the transition metals in the middle, like manganese here, you can see it has 3 different charges. That's as a result of the electron orbitals not being nice spheres. Things happen when you get that far into the periodic table. So you can see it can be +2, +3, or +4. All of the things on either side of it have all these wonky charges, and if you go down below here, you end up with crazy charges and stuff happening there too. So we'll talk about how we know which charge to use. There's some rules we'll follow, but for the very basic examples that we're going to be doing with Bohr models and Lewis dot, you're going to end up with things that kind of work out nicely. So sodium always has a charge of +1. You talk about the families always have consistent charges throughout them. So there you go. Could scientists do an experiment which would make it possible to gain 7, or is it impossible even in the lab? I'm not sure if they could or not. The problem that you run into is that the electrons that are kind of buzzing around the outside, they stick together with the positive charges in the nucleus. So you have those positives in the middle, and then you have the negatives buzzing around the outside. If I have like 5 positives in the middle, and then I have 5 positives around the outside, and then I add a bunch more, 5 negatives around the outside, if I add a bunch more electrons, there's nothing really to hold those electrons there. The charges are all kind of balanced out. So when we're talking 1 or 2, not that big of a deal. When you end up getting lots and lots of extra electrons, they really have no reason to stick because there's no more positive charge left in the middle. So they, fly off or they'll join somewhere else. So I'm not sure if they have or haven't, but the forces that hold those electrons on aren't really strong enough if there's not enough positive charge in the middle. Okay. We just did sodium and chlorine. That was kind of a really nicely worked out example. Let's do something that's a little bit trickier. I'm going to pick beryllium, which is a metal. So beryllium, I want to make sure I spell it right. Beryllium. And let's look at beryllium and nitrogen. All right, so what I would like you to do is repeat the process we just did for sodium and chlorine. First thing you do is draw the Bohr model for the atoms. Then you draw it for the ions, and then you try to figure out how they combine together. Now, I will tell you that this is a lot more complex kinda, than the sodium and chlorine example because you're gonna need more atoms. So what I would like you to do to start is draw beryllium Bohr model, draw the nitrogen Bohr model, then draw the ions, and then see if you can figure a combination of berylliums and nitrogens that'll kind of work together to make the electrons all balance out. I know you've never seen an example like this before, so just give it a go. But start with the Bohr models for beryllium and nitrogen. Beryllium's number 4 on the periodic table, and nitrogen is number 7. And that'll hopefully get you started. So what I'm gonna do, I'll just give you a couple minutes. I'm not even gonna put a timer up, but just go. I'm gonna give you a couple minute head start. I want you to try to do this on your own. At the very least, you should be able to draw the Bohr models for the atoms and then the ions with the square brackets and the charges to figure out if they're gonna gain a few or if they're gonna lose a few. So fly at that for a second. I'll give you a head start again. And then we'll talk about how they kind of combine together because it doesn't really make perfect sense. It's a little bit more complicated than the sodium and chlorine example we just looked at. Okay, hopefully you've got a good Bohr model going. So beryllium's element number 4, meaning it has 4 protons. It has a mass of 9. 9 minus 4 gives us 5 neutrons. So that goes in the middle of the beryllium there. Did I say boron before? I meant beryllium. Nitrogen 7 has a mass of 14. So 14 minus 7 gives us the 7 neutrons. For atoms, the number of protons and the electrons is going to be the same. So for beryllium, I have 4 protons. That means I have 4 electrons. First shell holds 2. And then the next shell holds a maximum of 8, but we only have 4. So there's only 2 left. So that's beryllium. Nitrogen, 7 protons means it has 7 electrons. So first shell has 2. The second shell should have 5. So I've drawn 1, 2, 3, 4, 5. There we go. Now, we need to ask ourselves, and this is where the brackets come in, Taylor. Beryllium, it really, really, really wants to have a full outer shell. Now, is it going to be easier for beryllium to gain, in this case, 6 electrons to fill its outer shell? Because its outer shell can hold 8. Is it going to gain those 6, or is it just going to lose 2? What's going to be easier for beryllium? Now, if I'm beryllium, I'm pretty lazy, and I'm thinking just getting rid of 2 electrons is going to be a lot easier than trying to gain 6. So we're going to lose 2. You guys are all on the right track there. All right, so beryllium, these 2 in the outer shell, they go away. They're going to go join nitrogen here eventually. And what are we left with? Well, we're left with a beryllium atom that's no longer an atom because it has lost some electrons. Now, before it had 4 protons, 4 electrons, but now it has 4 protons and 2 electrons. So maybe I'll write that down below here. 4 protons, 2 electrons. So what's my unbalanced charge between these protons and electrons? Well, it turns out that I have 2 extra protons. So beryllium is going to have an overall charge of positive 2. And I can always go to the periodic table and just verify that. So if I go look at beryllium, it's in the second column on the periodic table, and everything in that second column has a charge of plus 2. So I'm okay there. That's looking good. How about nitrogen? Nitrogen had 5 electrons in its outer shell. 1, 2, 3, 4, 5. Now nitrogen's kind of getting close to that middle ground. Now if I'm nitrogen, is it going to be easier for me to get rid of 5 or for me to gain 3? And hopefully we are on the right track, as most of you were for beryllium. Gaining 3 is going to be easier for nitrogen. Instead of losing 5, it's going to gain 3 to fill up its outer shell. All right. Now we're getting back to these brackets again. Why do I put the brackets in? Well, it's no longer an atom. The number of protons and electrons aren't the same anymore. We have an unbalanced amount of protons and electrons. Now, we have 7 protons. That never changes. It's always going to be the same for nitrogen. But in this case, the electrons has changed. I had 7, but now I've gained 3. So now I have 10 electrons. So what happened here? Well, I gained 3 negative charges, or I have 3 more electrons than I have protons. So this is going to have a charge now. It's going to become an ion, and it has 3 more electrons than it has protons. It has 10 electrons and only 7 protons. And yeah, you're perfectly right there. It's kind of getting confusing, right? Because beryllium, it only had 2 to give up, but now the nitrogen got 3. So where did they come from? So we're going to look at that here in a second on how that kind of works out. So these are the atoms up here, and these are the ions. So I kind of missed a step. Don't I have 9? Well, I had 7. Now I have 8, 9, 10. So I should have 10. And nitrogen on the periodic table has a charge of -3. So I'm thinking I'm okay there. Now, here's where we run into a problem. I'm going to take a little step back here. When we did sodium and chlorine, the sodium wanted to get rid of 1, chlorine wanted to gain 1. So it was all, it was all good. They wanted to get rid of 1 and gain 1. So you guys are all kind of identifying a problem here. Well, beryllium only had 2 to give up, but nitrogen gained 3. So how does that work? Yeah, we're totally running into a problem here. What if I added another nitrogen? What if I said, if I added another beryllium? If I said beryllium, I have another one now. Let's draw another beryllium, 4 protons, 5 neutrons. If it wanted to get rid of 2 more, well, I'm running into a problem here because beryllium wants to get rid of these 2, and nitrogen needs 3. So if I added another beryllium over here, and it's going to give up another 2, well, what's the problem that we're running into here now? The problem is I'm going to have an extra electron around. So it's not working out nicely. Not playing nice. So I had 2, and I'm trying to get rid of these 2. So let's assume this electron kind of hangs out over here with this guy. This one comes down here. This one's going to join this guy. And then this guy has no friends to hang out with. So what's going to happen here? So are we going to just keep doing this? Is this like the never-ending song? Is it just going to go on forever and ever? No. Alex, you're on the right track. If we have, as it turns out, if we have 3 berylliums, each beryllium wants to get rid of 2. So if there's 3 of them, we'll try to get rid of 6. If we had 2 nitrogens, each one wants 3, so if we have 2 of them, they'll each want to gain 6. So what I'm going to do is this. This is going to get really messy, but I'm going to go for it. I have 7 protons. I'm just going to simplify this a little bit for right now. I'm going to draw nitrogen, and I'm going to draw nitrogen. I'm going to have a beryllium. I'm going to draw beryllium. And I'm going to draw beryllium. All right, so this nitrogen, nitrogen normally has these 1, 2, 3, 4, 5. This nitrogen normally has 2. And 1, 2, 3, 4, and 5. Beryllium had the 2, and then it got rid of 2. Now, I'm going to kind of butcher this point to death, and it'll be so much easier when we continue on with this next day, so don't get too caught up in this right now. I promise it's going to get more straightforward. Beryllium's 4, right? So we had 4, there's 1, 2, I'm going to draw 1 here, and then 1, 2, and 1 here, and 1 there. All right, let's see if we can make this work. I'm going to take this, because it's trying to get rid of 2. That one's going to go there. That one's going to go there. That one's going to go there. Did I draw too many? Put it in the wrong shell. Doesn't help things. All right, so that guy goes there. This guy's going to go here. This guy's going to go here. And that guy's going to go here. So by having the 3 berylliums and 2 nitrogens is all going to work out together, and everyone's going to be happy. So I'll draw one last little final diagram here. I have nitrogen, I have nitrogen. So these nitrogens are now going to gain all these electrons, and they will both have a charge of -3. My berylliums have all lost electrons, and they will all have a charge +2. I'll draw in my electrons here in a second. What is B3N2? B3N2 is beryllium nitride. That's what we actually call it. What is it in real life? I have no idea what it does or what it is. I'm sure you could Google it. All right, whew, it's a lot of work. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. So that is literally the most complex example I can come up with for Bohr models. So if you're good to there, you're okay. And Abby, when you said, yeah, common factors comes into play, well, yeah, we have an overall charge of -3 and -3 together gives us -6. So we have to balance that out with +2, +2, and +2, which is +6. This is a lot at first. We're going to look at an easier way to do this next day because I've run out of time. But the idea is that there's easier ways to do this. As scientists, we don't use Bohr models. We need to use Bohr models at the beginning to kind of try to understand how this stuff works. Once we've kind of wrapped our brains around why the electrons are getting transferred in the ways they are, why beryllium's interested in giving up 2, why nitrogen is interested in gaining 3. Once you can kind of wrap your brain around that, the stuff we're going to do later on is going to make a lot more sense. So I'm going to, just for the sake of trying to get through some of this notes, I maybe throw up 1 or 2 more slides, and then we'll call her a day. Boron nitride. Boron and nitrogen are both, sorry Alex, I misunderstood your question a little bit. What is boron nitride? I don't know what it is. All right, so everything we've done up to now has been ionic bonds. Maybe I'll just jump. Yeah, I don't want to talk about that. I'm just going to start at the beginning next day. Why do boron, carbon, and silicon have blank charges? Again, good question. The atoms, when you get into the middle, like carbon, how many electrons does carbon have in its valence shell? I'm just going to get right out of there, so we don't want to deal with that right now. If I'm carbon, my valence shell has 4 electrons in it, which is a problem. So we're always like, well, is it going to gain or is it going to lose? Well, in the case of carbon, it's 4. So is it going to gain 4 or lose 4? It's kind of weird. It's in this like no man's land in the middle. So what happens is carbon, they don't have full shells. They have, 4. Carbon, silicon both have 4 in their outer shell. And carbon and silicon become really important elements, which we'll look at when we deal with covalent bonds. But generally speaking, because they don't know whether to lose or gain, they don't bond the way we've just indicated here. It's just not something they do. So they bond in a different way. They share electrons instead of transferring them. So that's kind of something that happens with carbon. Boron, same deal. It has 5 protons, so it only has 3 electrons in its outer shell, and it behaves as a non-metal. So there's lots of kind of things we still need to talk about before we can fully wrap our heads around that stuff. Let's just look at the learning guide, and then I'll set you guys free for the day. So we did nothing in terms of notes today, but I have a feeling we can probably, nope. All right. I'm just going to leave it at that. And you're thinking, Mr. Borden, you spent an hour doing something that we won't have to worry about. Well, yeah, you're going to have to worry about forming compounds. And I think it's more important to understand the why behind the things we're going to do next class instead of just kind of blindly taking them at what I'm saying. So forming bonds the way we did, then you're good to go. But it's not anything in the notes, or there's no examples based on it. So I want you to just kind of understand the how behind it. We will continue on with this next day. For those of you who are all caught up, awesome. And if you're not, think of this as a great opportunity for you to get caught up, because there's nothing really to do for kind of work beyond what we did in class today. So there's nothing from the learning guide. I mean, you could go through the notes on your own and try to, get a bit ahead, which is fine if you're just looking to do some work, but take a break maybe. We'll continue on with this stuff next day, and we'll start to get into some more new stuff. Yeah, just reading your question, Alex. Can they just loan them? They share them. They don't loan them and expect them back. They just share them. It's like, hey, let's just share these things and we'll be good to go. So that's it. Hopefully you guys can come to McWilliams tomorrow. I forget what time the virtual field trip, I think it's like 10:45 or 11 or something like that. We're going to connect with the Palm Beach Zoo. I've never connected with them, but it should be good. And yeah, hopefully we'll see you tomorrow. So have a great afternoon, guys. If we don't see you tomorrow, I'll see you on Monday. Thanks. Bye.